piece of it. So I've got COVID, but it's real low grade. You can see that I'm surviving pretty well, but I didn't want to give it to anybody. The last 2 years, all this was done by Zoom, and it was certainly worth doing. But the original intent was to get you folks into Penn. You know the song in Hamilton, that you want to be in the room where it happens. You are in the room where it happens. You study science for most of the time that you're in school. I don't know whether you ever have a sense of where that information in the book comes from. Like, how do they get that? Well, you're sitting right in a building where they get the information that's in the book. And in fact, you're at what might be the most technically interesting intersection in the country. You're at 33rd and Walnut Street, and the building you're in is the David Rittenhouse Laboratory. That aerial photo shows you where we are. Okay, Walnut Street runs horizontally there, with West Philly to your left and the river to your right. So the David Rittenhouse Laboratory is named after David Rittenhouse, who kind of took over as the head of science in the United States in colonial times after Ben Franklin, who founded the University of Pennsylvania. Across Walnut, or across 33rd Street from where you are right now, when you leave the building, if you look across the street right on the corner, there is a big rectangular brick building that started life as a factory. But in the 1940s, they built the first digital computer there, the ENIAC. This is where computers started. So it is really a tremendously important historical area. The building, in those days, they didn't have transistors. They had vacuum tubes. And I don't know, this is actually one of the tubes that would have been used in ENIAC. It's a 6SN7 tube, and it does what today we do with 2 transistors. The ENIAC had 18,000 of those tubes, and they burned out about every 10,000 hours, which meant that every half hour a tube died and they had to find it. Your Mac Pro with maybe a Core i7 processor has 3 billion transistors. So luckily, they got these things to be small. And computers have just gone on like crazy. But it all started right across the street. And that computer with 18,000 vacuum tubes took up the whole first floor of the building. If we take a look at, go catty corner, so we are across Walnut Street from David Rittenhouse Laboratory. We have the Laboratory for the Research into the Structure of Matter, LRSM. It was built in the 70s when they realized that the new discoveries were going to be found in between the sciences. That if they combined what they knew about physics and chemistry, they would be studying things that no one had looked at before. And so that's what the Laboratory for Research into the Structure of Matter was all about. And one of the things that they did there was they developed plastics, transparent plastics that conducted electricity. At the time, it wasn't clear how valuable they were, but by about the year 2000, it was clear that they were extremely valuable, and the people who made that discovery were awarded a Nobel Prize. And it is a big part of most of our computer and video technologies these days, that we can have flexible plastics that have electrical capabilities. If we then come back to our David Rittenhouse Laboratory, in the mid-1960s, Ray Davis started an experiment to try to check on neutrinos coming from the sun. Excuse me, apparently I have COVID. And it turned out they had predicted that the sun should send out neutrinos. When Ray Davis looked, he only found about 1/3 as many as astronomers predicted. This was in 1968. It took 35 years, and this is the important thing to appreciate about science. They don't just say, oh, look, here's what he says, let's put it in the book. They check and check and check and check. 35 years later, they figured out that Ray Davis had not made a mistake. There were not as many neutrinos as they thought, and it was because they did not understand how neutrinos work. That's a big thing. It changed the way we understand elementary particles, and Ray Davis won a Nobel Prize in 2001, 35 years after he did his first experiment. So this is hard-won information, and this is a really neat place to be. And I should say, that all sounds like, a lot of you were born after any of this happened. But in 2012, again, work here at Rittenhouse Laboratory made a big, big advance. The Higgs boson was finally observed at the CERN atom smasher in Europe. But the detectors that actually showed that they had accomplished that task were designed and built right here in Rittenhouse Laboratory. In fact, just down the hallway from where we sit right now. So this is an active research lab, and you really are in the room where it happens. We could also point out that what's going on here right now, in this next slide, Jean Malie and Charles Kane are working on topological insulators, which are materials that only conduct electricity on their outer surface. They don't conduct electricity inside. And this produces some effects that might let us get to quantum computing, and they won the Breakthrough Prize in Fundamental Physics, which is 3 times the money of the Nobel Prize. I mean, it is a really big award because what they discovered is a really important thing. So this is really an active place right now. But now if we go to that fourth corner, as I say, I used to complain that this was space that we had not, that we should be doing some marvelous science here. And Peter pointed out, well, no, they're doing even more important stuff there, because that's a dorm. And that's a place where students stay so that they can study at the University of Pennsylvania. And it really rounds it out. Science is A, figuring out how nature works, and B, telling other people about it. And so that dorm is the place where Penn is doing the rest of that work. And it also gives you a place to be at this intersection, because if you come to Penn, you might actually stay in the Hill House dormitory. And so now you know that this is why it's worth coming down here and not just Zoom. When you walk out, take a minute to feel the place that you're in. Look around that intersection and think about the intellectual energy that's happening all the time. It was always a joy for me just to be there. And we're hoping you get a little bit of it while you come down here. Thanks for letting me fit into this program, and I'll pass it back to Mary and Peter and Ryan.
Thank you so much, Phil. This is my other show. This is a brand new show. If you wanted an excuse to have a field trip every single year, this is now our 4th show. So you could come here every year of high school, get your teachers to come, and they would never see the same show twice, which is pretty exciting. But so we are not going to explain everything to you in full detail. You are going to leave with lots of questions for your teachers. What we are primarily going to focus on is energy, which crosses every single topic that you talk about in your science classes. And so the details that we don't explain here today, you can come to next year's show, or the year after that, or the year after that, and we'll talk about it more. All right, so what do I have here? I have a Newton's cradle here. You can go buy this at Spencer's, just don't look at anything else that they sell there. And we're familiar with this. We pull one object up, and one object flies off the other end. We've seen this before. There's a concept behind this called what? How many of you have learned it already? Well, I heard it. Momentum, right? There's a thing called momentum here. Why is it that I can't send in 2 orbs and get 1 orb off twice as fast? Wouldn't that keep all the momentum things the same? There's a mass and velocity thing happening here that has to be the same on both sides. Why couldn't I just be like, hey, boom, and launch 2 balls off the other side but slower? right? And momentum isn't everything, is the point. There's this other constraining factor called energy, and that's what we want to talk about. How do you know when something has energy? If you have little siblings, you know. Right? Right? Oh my God, they're right. Right? They're moving everywhere. They're going fast. Oh my God, my kids on New Year's Eve were sugared up. It was insanity. She wasn't. But the rest of them were sugared up and it was insane. Right? And how did I know when they were out of energy? They sleep so fast. Right? And so we know that there are these things that have to do with energy. And I've left all the notes up from dress rehearsal yesterday that Pete is politely blocking. But so I want you to have a couple terms put together because I can't have you block them all. Thank you, though, for protecting it. When things are moving, we're going to call that kinetic. Now, I don't care which way it's going. I care that it's moving. Faster is more energy. Slower is less energy. And that's a thing that we fundamentally know, right? But what if I take, and crud, I don't have anything. What if I take this, and I'm so sorry, I forgot something. What if I put this here? It's not upsetting for the rest of you, it's upsetting for you. No, well, but there's a trust level here, even though there's no reason for you to trust me. What about now? Oh, this is more upsetting, right? Right? How come it's not moving? It's potential energy. It has the potential to move, right? And that's a little bit scary, right? And so when we take things and we change their position, we are storing energy there, right? So the positioning of things has to do with storing energy in a place. The higher it is, the scarier it is, right? But we also know the heavier it is, the scarier it is. If this was empty, I wouldn't be too worried about it, right? But there are other things going on here. Like I have these weird props out here. What is this about? Pasta. What if there was a pixie stick? What do both of those symbolize for you? Right, carbohydrates, energy, right? Sugars are these long things that are really easy to break down. So they give you fast energy. Chemical energy is stored, it has potential in the position of the atoms, right? It has stored energy. I know, Joe, watched you teach an entire unit on nutrition. And but what about this? What is this about? Fire, right? Oh wow, no, not this one. This I don't know if this is the one I picked. All right, well this doesn't work. There's no fire, right? But when things are warm, right? There's an energy to that. It doesn't look that way, right? Because I know that Bill had a fever for at least 2 days, and he laid like a lump, right? He wasn't moving, but his temperature was up, right? So something was going on energetically with him there. My point is that not all of the energy is something that you can see. You don't look at pasta and go, I'll bet you that'll give me a boost, right? You don't look at like meat and tofu and go, that has protein. That's going to give me an energy boost. That's non-mechanical energy. But you can't see it when it's stored in the particles. It's non-mechanical. Thermal energy is moving energy, but having to do with the particles. Literally, when you have a fever, all the particles in your body are moving faster to try to get to the source of your infection. That's why you have a fever. Because your temperature is going up because everything in your body is moving faster. It doesn't look that way, you're just a lump on the couch, right? Other things that I have up here. I think my magnet is gone, but I have this guy, my Tesla coil, that we're hoping doesn't short everything out. We are not sponsored by Shabani or San Giorgio. Thank you very much. There's clearly something happening here. Right? The light bulb isn't moving. But there's clearly something going on with energy here. This is electromagnetic, right? This has to do with the behavior of charges, right? Magnetism has to do with magnetic spin on electrons. Electricity has to do with the movement and position of charges, right? And then the last one, we're going to cover all of these today in some, oh, that's the wrong one. Jeez Louise. Is light, right? You saw the laser pointer pointing at stuff. Light. Light is another source of energy. Non-mechanical, because we don't see things move. I'm just moving a laser, right? It's not that exciting. But this has to do with the movement of photons, right? So energy, we know what it is. We know when we have it. But when we go to define it, it becomes this very bizarre thing. This is all kind of all over the place, right? If we go to our textbooks, our textbooks have very incestuous relationships. They go, energy is the ability to do work, and work is the transfer of energy. Well, I don't know what either of those are. What good is that definition, right? So then you go to Google, and Google is all this bull, right? Like, what is that? The strength and vitality required for sustained physical or mental activity. Okay. I don't know what that means. That doesn't help me lift the box to the top of the shelf, right? So what I want you to think of energy as is a quantity related to the condition of an object, right? A child running around has energy. When that condition changes, right, they've done some kind of work and expended energy, right? When you eat food, you've changed your condition and gone from, potentially hungry to not hungry. It depends. There's a lot of teenagers in here, so it might never cap the hunger. I don't know. But growing is hard. But when we change the condition of an object, though, we've done work. So a thing has energy based on the condition it's in. When we change that energy, we change its condition, we've done work. And those are the overwhelming thoughts that I want you to have with you as I hand things off to Keith. And I unplug this. Ellie, bring in those words.
So, I'd like to spend a little bit more time with something like the Newton's cradle. But you came all the way down here because we have ridiculous toys. So we might as well switch to, a theatrical version of this. We'll bring that over here. Right, and so we have a bigger pendulum that we can talk about, just because, we like to play with the people in the back. So, to do this demo right, I kind of have to get the aim just exactly right. All right, so, the important question here is, why was I not freaked out at this thing rocketing towards my face? Right? So, it clearly had a bunch of energy. We've already talked about this, right? When the pendulum is all the way over here, what kind of energy does it have? Right, it has potential energy, right? We've lifted it up, it's heavy, right? It has potential energy. When it was down here, at the bottom, what kind of energy does it have? Right, it has mostly kinetic. If we want to get really specific, it still has some potential because it could fall into the basement, right? But it has mostly kinetic. And then when it came over to this side, just before it changed directions again, what kind of energy did it have? Potential. It had potential again. So we went from potential energy to kinetic energy, back to potential energy, presumably back to kinetic, back to potential. Why was I not afraid of that kinetic energy, even though my face was right here? Right? That there's some distance that I know I am, right? How did the ball get back up? Right? That it had kinetic energy down here, and then it somehow got potential energy again. Where did that potential energy come from? Energy always stays the same. Right. So that kinetic energy could turn back to potential. But could that kinetic energy come back to a higher potential energy than what it started with? No. This, you hear this referred to as two different things. One of them is one of the laws of thermodynamics, which is that you will never gain energy out. The better way that we want to talk about it is the law of conservation of energy. Right? A conservation law is a ridiculously powerful thing in physics. Right? Because a conservation law says that whatever the initial conditions are have to be the end conditions. And a much more practical to you kind of way to talk about that, it means you can always check your answers. Because you know starting conditions have to sum up to be the same as the end conditions. So regardless of what was going on in the middle and how you were calculating things, you already know what the answer is going to be, because it has to be where you started. So in this situation, we had potential energy turn to kinetic, turn back into potential, and we knew that that sum of energy was about the same. We saw that by that height. Right? We can also do that the other way around. If I have a ball, and I throw the ball in the air, it has some kinetic energy to start, then it reaches the top where it's not moving anymore, it just has potential energy, and then it drops back down. Based on what I've just said, about how fast do you think it's going when I catch it? It's going about as fast as how much I threw it up, right? But I threw it with some amount of kinetic energy. All of that became potential, and then at that same spot, it's all back to kinetic again. And we end up with the same speed on both sides of that. So from this idea of kinetic energy, right, potential energy switching back and forth, we could talk about this in other forms as well. So just to go slightly more complicated than this, we have a loop-de-loop. So if I start the ball here, will it be able to go through the loop? No, why not? Right. There will never be enough energy to make up that potential energy. So, if I want to start this, so let's start at the same height as the loop, right? Oh no! Why didn't that work? All right, so I heard friction because that is the place we always say first whenever anything doesn't work, right? But more importantly than that is there are some energies that we're not paying attention to. Did everyone hear that sound? Sound is an energy, right? That's a motion in air. So all the energy of that sound has to come from that starting potential energy. This ball is heavy and was spinning. It takes energy to spin the ball. So all of the energy necessary to spin the ball had to come from that starting potential energy. So if we know that those energies have to go places, we can just account for them, and we can start at a higher spot. All right, and make the loop. Because we know that the energy it takes to spin that ball is about that much more. What's really important here, and this is what takes it from the law of conservation of energy to like the laws of thermodynamics, right? Is that energy cannot be lost. Energy cannot be gained. There's a finite amount of energy. If you are ever doing a situation where it seems like you have gained energy or lost energy, it is because you are not looking at a big enough picture. And the energy that is missing and unaccounted for is now just outside of your frame of reference. Right? In that first case, it looked like we were losing energy because we weren't looking at the sound. We weren't looking at the spinning. So those energies seemed like they disappeared because we weren't paying attention to them. Now, as you can imagine, I've been doing this for a while. You probably don't exactly trust me with some of these things because, maybe I could just take a punch to the chin really well, and this actually did wallop me. So, to reinforce this, we're going to go to a demonstration where you know it can't flinch. Right? So this is just a pane of glass. And I'm going to bring this up right to where it touches. And we're going to look up.
Why am I back here?
All right, and it didn't hit. Even more than that, I now know that there's a gap here, right? Because there is going to be some energy loss in that system, right? That we know that even though it's starting here against the glass, there's a little bit of noise up there, right? There's a little bit of heat coming off of that rubbing. It's always going to be losing energy, right? The only way that we could have more energy in the system is if we do something like starting with a higher amount of potential energy.
I'll get back.
Right? And we know how much energy is actually in the system. So, we are now in a situation that is a definitions of energies that were kind of words, and you kind of knew what was going on. I've now shown you a little bit about energy, how it can move around, things like that, but we still really haven't gotten to talking about what is energy, what are defining characteristics, how do we talk about these things. So to go on to that, we're going to pass this off to Ryan, who's now going to talk to you a bit more about some specifics of how this energy is doing the things we say it's doing.
And
We will have to put this on for a minute to focus it, but we can do that when the time
how did I get stuck following breaking glass?
comes. Fair question.
All right. All right, energy. As alluded to earlier, we love it because it's like this universal binding concept that we all say because it's true, it is. Also alluded to, you know those Newton's cradles, we love to play with them, my kid loves to play with hers. But you only get one ball in, one ball out, 2 balls in, 2 balls out, 3 in, 3 out. You can't manipulate that situation to have a different kind of thing coming out the other side. Follow me? Energy, understanding it would be really great if we could then take energy from one thing, one situation, and do another thing, and do another thing, and do another thing. So, Pete's talking about kinetic and potential. We all start with the really rudimentary thing, pushing a boulder up a hill takes energy. Don't be Sisyphus and keep doing it even though you're not accomplishing anything. So, it's well established. You can put energy into the system, originating in the food I ate earlier, lift the ball, and unleash that potential. You get movement from storing up high. And if I want to repeat that, I got to grab the ball, lift it up again, let it go again, lift it up again, let it go again. You're hammering a nail, right? You can't walk away when something's hammering your nails for you. Yeah, some of you know you can. But you don't get any of that until you start exploring moving energy from one place to the other. So I've rigged up a turntable with these little rubber sockets that I can place at the bottom of my ramp. So this thing can spin, right? Mass is in motion, that's kinetic. I can store some potential. It has a linear movement. I can turn that movement. The steel cable with the heavy, heavy ball at the end was working to turn that ball in a trajectory, right? The ramp can turn my ball. Let's see what happens. It's not going to be a huge surprise. This may seem trivial, but it's actually kind of key. This is a really different way to have energy than just having something barreling down the tracks. Does that make sense? I can turn something from linear motion into rotation. And that's key, because if we're going to start powering machines, we need spinning wheels and stuff like that. And it matters a lot where we try to get the mass moving. It's not a Winter Olympics year, but have we all seen the figure skaters going into their tight spins at the end of the routine? They pull in their arms, they get fast. They push out their arms, they get slow. We can change where the mass is in this setup. So same amount of energy in, right? If I've lifted the same thing to the same height, same amount of energy, I let go, fail. Didn't aim properly, yeah. Seems to do a little less, it's slower. 2 reasons. What's winning out is that if I do the same collision closer to this axis, I'm pushing less hard on the whole thing. But what's weird is I'm pushing less, torquing less is the word, but I'm doing it on a mass system that is now all closer to the middle. Key takeaway, energy isn't directional. I can take it from being this thing, stored potential, to fast down a ramp, to spinning. And that shows up in a really interesting way with a thing called the Wilberforce pendulum. So the nature of a spring is that it's this hunk of metal cleverly coiled around. You stretch it, slinkies are fun. More weight, more pull, more stretch. But if you stop to think about it, if you stretch this thing, however round, the size it is in this dimension, has to be smaller to accomplish that stretching, right? If you're only set with so much wire being coiled, if you make it a long straight wire, you lose radius, lose radius, lose radius the longer you stretch it. That's interesting because, believe it or not, if you twist a coil like this, it wants to go back. It's springy in two ways, right? You can make it longer, or if you twist it, it wants to go back. You're not here to take our words for it. I twist it. Nobody has a wind-up watch, do they?
They have iPhones.
They have iPhones. I haven't wound my iPhone.
Yeah, they can time it, is my point. They just can't.
Yeah. Yeah, we used to have a clock in my house that you had to wind up. Store potential. So I tried to start it with only stored rotation. What's happening when I let go? I didn't really tell it to bob up and down this much. That's weird. I can change that kind of stored energy, much like the ramp, into a bobbing kind of energy. And if we keep watching, spinning and bobbing, it's a mixture. I've stored energy as a rotation, a wind-up. Ooh, now it's barely bobbing. It's back to how I started it. Every time the spring stretches, it's putting, I'm going to throw out a word at you, torsion. It's twisting the spring in a way that wants to elongate it, but it wants to go back how it used to be, right? And it's this feedback loop where it's pushing in the right way at the right time to take some of that twisting energy and turn it into bobbing energy, and back and forth and back and forth and back and forth. And that is really key. We don't use a lot of machines that run on this exact mechanism, but it's a good way to look at and visualize a way to have systems that keep moving back and forth between two kinds of energy. And I've got another one. Let's just see what this looks like. And it kind of points out that different springs need different mass setups. If the spring is stiffer and different in that way, that looks like a weird contraption, right? You have to configure the mass like that figure skater in a way where the spinning wants to happen at a certain rate that's tuned in with how stiff the spring is, and I'll leave it at that. Now the teachers have to sign. All right, energy transfers. I didn't break anything, but conceptually this is really fundamental.
Oh, right. So now I'm going to start to talk about transferring energy. And we're going to do a couple different things here. Can you get that plugged in and set? So we're going to do a couple different things here. Sorry, my back is to all of you. You can get a ladder out here. And Ted, I'm going to put this ladder pretty much exactly where you are. And two people we did not introduce along the way here are Mr. Ted Knighton, who is a cinematographer that works for the university that has been kind enough to be with us today. And my daughter Ellie is floating around here doing about 1 million different things for us today. All right, so what do I have here? Janky cleaning gloves, right? Just janky cleaning gloves. No. I do what most people do with their janky cleaning gloves. I've filled it with lead shot. That seems smart. And I have here a Lager Pro thermometer, and I'm going to stick this in here.
We're on the wrong screen.
Oh, wrong screen. Jeez Louise, because I'm dual screening. I'm sorry. I got it set up on one screen, but not on the other. Let me just drag Lager Pro out here. There you go. But, so I'm going to take this Berner digital thermometer. I'm going to stick it into the lead shot in here. Just for proof of concept. This is room temperature, right? Maybe a little cooler. Actually, I was holding on to the thermometer before, so at the part of my hand that actually produces heat. So take note of this, 21.8 degrees Celsius. Now we're going to seal this thing off. Thank you, sir. Thank you, sir. And we are going to tag team this job here.
14.
And we're going to drop this 15 times. 2. You guys can feel free to count along.
3.
And it's helpful because every time I lost count. It's like in Derby, they tell you to say it fast and I forget.
7. You guys are so good.
We're almost there. A lot of people in this room are elementary school. What are we on? 10. Woo! Because I already lost count. You guys are actively counting. 11. Right.
Doing the fingers. Doing the
Right,
fingers.
2 more. 15. All right. And now, my beautiful assistants are going to go ahead and get this measured again. What have we done? Oh my God, we broke it. We broke the lead shot. No, we didn't break the lead shot. Yeah, I don't really think you can break lead shot. I don't think that's a thing that can happen. I feel good about this. That look good? All right, cool. All right, so what have we done? How did the lead shot get warmer? I didn't cook it. Right? All I did was drop it. Right? This is a terrible way to cook eggs, by the way. Don't do this at home with eggs. Or lead shot. Oh my God, we spilled some and it was terrible. So what happened? I took mechanical energy. I took moving energy, right? Well, first it was potential, then I converted it to kinetic, and it became thermal. Every time we had one of those collisions, the lead shot all hit each other. Oh, I need this guy first. I almost forgot. Yep. The lead shot all hit each other and sped up the individual particles of lead. All right, and so here we have a little model for this. This is a function generator that is cued right now to 10 hertz. So it's going to vibrate 10 times in a second. But the amplitude is at 0, so it's basically it's not loud right now. And it's aimed oddly in a weird spot. All right. Is that visible enough? Yeah. All right. So I'm going to give it a little bit of volume. And you can see the particles moving in it. Right? If I can get them moving faster, what do you expect them to do? Take up a little more space? Is that reasonable? Right? This is effectively a model of what's happening on the molecular level with particles. Right? When they collide with one another, right, they're transferring energy between them and they're able to take up more space, they're able to move faster, they make the thing warmer because they're able to move more. And so this is just like a visual because one of the biggest challenges that all of your teachers have when we transition from mechanical to E&M, right, is that you can't see it now. Now it's like, well, we're just making it up. Yeah, that's the protons are all in the middle because, Rutherford did a thing to prove a different thing, and it turns out he was wrong, right? So we like to put in models wherever we can to see stuff. But all right, so we can take mechanical energy and we can turn it into thermal energy. Can we take thermal energy and turn it into mechanical? Let's check and see. So this thing is about at the level of my hand. I am not going to set this. Oh, I'm moving the meter stick. Am I touching the meter stick? No. I'm warming up a rubber band. That's a discussion for your teachers. Why heating the rubber band actually made the rubber band contract instead of expanding it. That's a discussion that your teachers are going to have to Google later as well. Exactly. But my point with this is that, we need that other cart over here.
Yeah, it's coming in now.
But my point with this is that we can, that entire concept that energy is energy is energy is energy, We can transfer energy from one form to another. One of the things that makes science so good is that it has this double check. What do your physics teachers tell you on the test? Double check your work, right? If you're not sure, you can work it backwards. There's probably a second way to calculate it. Physics has that. It has the law of conservation of energy. But what they taught you in middle school is, oh, hey, you can go ahead and double check your work, but like energy can be neither created nor destroyed, and that's it. And here, we want to emphasize to you, it can, however, be transformed into other forms, right? That thing that Pete said, that none of this stuff happens in a vacuum. If you think something spontaneously has energy, you're not looking at enough of the system. So here I have 2 canisters, and I'm just going to do this weird cryptic thing, and we're not going to talk about it again until after the break. So I have here a canister that is filled with air, right? And I have a canister here that is about to not be filled with air. Oh, God, I hate this. Okay. This is now filled with CO2. How can I be sure that it's filled with CO2? It's the difference between CO2 and just CO. CO2 is dense. It'll stay at the bottom of the container, right? So I've filled that thing. You can a little bit see some foam in there. I'm going to cap this off so that it's filled with air. And then while Pete's talking to you, I'm going to put a heat lamp in between the two. A heat lamp gives off infrared light. It gives off visible light, but it also gives off a whole lot of infrared light. And I'm just going to let this sit and not explain why for a little while. You know, which is not sciencey, but we'll get there.
So, unfortunately, one of the things that's really true in science is that we have very specific language, right? That's why we get into these pedantic arguments with people. And unfortunately, heat can mean 2 completely different things in physics depending on how you're talking about it. So when you say heat, right, like the fire has a lot of heat and I'm getting a lot of heat from the fire because it's heating me up. Like, that's not specific enough for physics. So we have to talk about it as something has thermal energy. It is hot. It is then radiating heat somehow, and the way that we normally think about that is by giving off IR light. IR light, infrared light. Right? So that is, it's light. It's all it is. It's light. But it is light that we cannot see. Why can humans not see IR light? Because there was no evolutionary pressure for our eyes to develop IR vision. Right? There was no reason for us to do it. Our skin is really good at sensing heat. We have pretty decent color vision. There was no reason for our eyes to get good at that. Right? There are things in the universe that did feel that pressure. Vipers can famously see heat. So can the predator, right? But we, being amazing tool-using things, have developed the ability to see infrared light by making cameras that can see infrared light. And that is what this is. This is a thermal camera. So, to be very clear, what you are seeing right now is not IR light. This camera looks for a specific wavelength of IR that it knows is reflective of how hot the object is. It then does some calculations and figures out what the temperature must be so that it produces that light. So, IR light is not on a spectrum from white to black going through yellow and purple. That's not how this works. That's there so that you can see what's going on. But we have this thermal vision, right? And we can see people produce heat in ways that we expect.
Your hands are cold today, too.
Right? Faces are pretty warm. Eyes have lots of hot blood in them, so they are very hot. Right? Our clothes have a lot less. Right? If I step between them there, we can see that my nose is a little dark. My facial hair is much darker because it's away from my skin. Right? We can see that my clothes are darker, but if I take my hands and warm up my clothes, we can see handprints on it, right? So we can see that change in temperature because we are looking at this IR light. Now, so this is light. We can play all kinds of light games with it. For example, say I'm hiding from a viper or the predator, right? And I don't want to be seen. If I'm hiding from you, right, like the trash goblin I am, I can just like get in a trash bag and you can't see me, right? But if I stand in thermal vision, doesn't really help, right? This is a thin piece of plastic. It is opaque to visible light, and it is nearly transparent to IR, right? On the other hand, let's say that I don't want to hide from you, right? I want to be seen, but there needs to be something between us. I don't know, for some reason we have to be at least 6 feet away, or there needs to be a solid object. I don't know. Things like that happen, right? But if you're the predator, you suddenly can't see me through this pane of glass. Why? Why am I suddenly hidden behind this pane of glass? Because that's what we designed glass to do, right? Right. Here's some good explanations of the science out there, right? But more or less, the short answer is, we developed glass because we like to look outside and not have to also heat the outside. So we developed a material that is transparent to visible light and nearly opaque or reflective to IR light. So the inside of your house stays hot or cold, or I don't know how to live. And the outside isn't affected by that temperature, but you can see through it, right? So all of this is some nice ways that we can think about how this energy is going around. There are a lot of these energies that are hard to wrap your brain around because you've never seen an electron, right? You've never seen atomic things moving around, but it's there, and with the right kind of technology, we can see that, right? So just to kind of hammer this home, pun intended, sorry, we're going to do a quick demonstration here that is replicating effectively what we saw with the lead shot.
You want me to touch the plate because my hands are invisible?
Sure. You gotta stick your hand in, right? So there you can see a plate. It's on the table. We can see Mary. Right now, the way the scale has been working this whole time, the hottest thing the camera can see is white. The coldest thing the camera can see is black. And it has been always switching around based on whatever it's seeing, right? Which is why you're starting the colors jump around a bit. For this next bit, I've locked off the temperatures. So now we are really looking at this plate, right? And what kind of energy is on this plate, right? So when we did the lead shot, we dropped these pieces of metal from roughly, let's say conservatively, 12 stories in the air, right? They hit the ground and had all of this energy. We took potential energy, it became kinetic energy, which became thermal energy on impact. We did the exact same thing on a much shorter time frame with this plate. So as we can now see, one part of that plate is suddenly much, much hotter. Because I put a ton of energy into it in a very short amount of time. Right? All of the kinetic energy of this hammer went into the plate. And since the plate is a good insulator, it is now held on to all of that energy. There's a lot going on here. We have covered a lot of stuff. We've covered so much that I feel like it is probably time that we let your brains digest this a little bit. And we are going to go to intermission.
not really sure why I did that. Can we video mute, please? On the big screen, okay? We're not really sure why I did that. And so, what in the world is going on here? These two canisters are exactly the same, except one of them has CO2 in it and one of them does not. They have not been heating up for as long as I would have liked because it turned up at the last heat lamp was broken. I don't know if you noticed me jump back there, but there's something loose back there and I got a little shocked. So we got the heat lamp out a little late, so it might not be as dramatic an effect. But right now, Pete is taking a look at the temperature difference between these two canisters. These canisters are optically identical to you, right? They both are filled with a clear gas. One is air, one is CO2, right? But what do we know about CO2? Right, and some people will call it greenhouse gas, right? It absorbs infrared. It absorbs heat, right? And so we're using this infrared light. We're sending it into these clear, thin materials, right? We're allowing it to pass through. And what you can see, it's not as dramatic as we would have liked because the heat lamp wasn't on for as long. But we can see a little more warmth than this guy. And every once in a while, you can actually see the CO2 move in there. But we might need to narrow the scale a little bit. But
6.9.
yeah, it's already cooling down. I think they're probably already cooling down. But so the idea is, and I'm sorry you're not seeing it today, there's an amazing paper in the physics teacher that you can read, written by Dr. Phil Nelson back there, where they have magnificent photos of this. And if I try to remember, I might send them to your teachers later. But I also might not, because sometimes they disappear when the semester starts. But the idea was that you were going to see that the CO2 canister was significantly warmer, by like a couple of degrees, right? And it sounds like it's not a big deal, but over the course of a very long period of time, it becomes a very big deal. Like in 1914, they wrote a little blip. They were like, we need to fill in this little bit of newspaper. And what are we going to fill it with? And they were like, what if we filled it with this little article about like how now that we're making automobiles, there's more CO2 emissions. And that's warming stuff, and isn't that weird? This is back. No, it's not backwards. All right, cool. And so back in 1914, when there was no political impetus to any of these things, they were writing about how CO2 is like a blanket, right? When you lay under a blanket, you pass your infrared energy, right? You pass your infrared light off to the blanket, and the blanket can store that heat, right? And without a blanket, you get cold. With a blanket, you get warm. CO2 does the same thing. I'm sorry you didn't get to see it as well here. But we have other cool stuff that we get to light on fire. And so, Ellie, can you...
No,
you got
okay.
it? It's all cute? All right, cool. So, what we want to talk about here is this transfer of energy. That was transferring energy into canisters filled with different gases. Now we're going to send energy across a distance, right? So I have another one of these heat lamps. It's making visible light, but it's also making infrared light. And then we have these things that kind of look like satellite dishes or mirrors, but you wouldn't do your hair in this. It's not, if you got to look at it at all while it was over here, it's not shiny. You can't see very well in it. So it's not for visible light, but it's really good with infrared light, right? And so I have this heat lamp here, and it's hot over here. And, we actually pointed the thermal camera at one of these by accident yesterday, and we almost killed the thermal camera because it's so hot that it almost blinded it. So I've got something here called flash paper that if we bring flash paper close to a heat source, should catch on fire, right? And fairly easily, but it's not over here, right? It's not even a little bit. It's just sitting there near the heat lamp. Now I'm going to bring it down here to the other end. This light is exactly at the focusing point of this mirror. And what does that mean? That means that the light is filling up this mirror and it's sending parallel beams of light all the way to this other mirror and bringing them to a point right here, which I'm using this thing because I've burnt enough fingernails on this. All right, we have that there. Do we want the lights out at all? I need the lights out for this, actually.
Yeah, I got you.
And what I'm looking for on here is an image of that heat lamp on the paper. I used to do this in my hands, but it really burns my fingernails. And so yeah, I had this right next to the lamp, and it wasn't catching fire. But I was able to take that heat, that energy, and that infrared light and send it all the way across here and focus it so that it lit this paper on fire. right? This is what's happening with your satellite dishes. Very exciting. But this isn't the only kind of energy that we can send long distances, right? Does anybody live exactly right next to like Limerick Nuclear Generating Station? I actually used to live like right next to Limerick Nuclear Generating Station. But does anybody live really close to a power plant? Right? Like within eye shot, maybe? But odds are that's not the power plant you're getting your quote unquote power from. Your power companies are actually energy companies, right? It's Pico Energy, Pennsylvania Electric Company Energy. Pico is selling you energy, they're not sending you power, right? So what I have over here is a kind of broken down sort of transformer. I'm going to take a magnet. Remember, energy comes in all these different forms, mechanical and non-mechanical. I'm going to take this magnet and move it. And oh gosh, nothing is happening over there. I failed on 2 demos! No. This guy's not plugged in. What if I connect it? You see it starting to move? I didn't do that. I didn't touch that spring. This magnet's motion is forcing electrons to move in that coil. It's going along these wires, forcing electrons to move in this coil. And then that's forcing the magnet to move. Right? And again, your teachers can explain all of that. Or you can come to our show in 2 years on electricity and magnetism. But we're able to send electrical energy, light energy, heat energy. Have you ever taken a lens and lit ants on fire with sunlight? Right? The sun is sending you energy. Also, that's the first sign that you might be a psychopath.
Or a scientist.
Or scientists, right? It's alarming how quickly our students light stuff on fire. But so the point with this is that we can send energy across great distances, right? And that's very important. So we can transform energy, we can send energy, and now I really can't remember who I'm handing this off to next. Awesome. Oh, and I'm moving the wrong card.
Yeah.
All right, so I'm going to hand things off to Ryan, who's going to talk to you about timing.
Okay. So Mary raised the idea of the electric power plant, right? Energy, now it's in the realm of our everyday lives. We love to, well, we don't love to vacuum, but it's kind of essential. We like dishwashers, we like televisions, all these things, like you name it, thousands upon thousands of devices. It's all based on this ability we have to deliver energy to the wall socket in your house. You can harness it and use it at will. There's a long history of how we got from nothing to that. And it all kind of started with this magnets in the coils thing that Mary showed. And we're saying energy is conserved, and we're saying that like electricity right delivered to the source is this amazing thing. I was a Costco member for a little while, and I'm wheeling my cart, this is like 12 years ago, and you know, there was a display, Vitamix, and one of the ways they're trying to hook me in as someone who seems like an adult and like makes soup and things, is to say, not only can you chop up frozen fruits, which is hard to do, but if you just put your soup ingredients in there and let it run for a few minutes, you'll get hot soup at the other side. And being a physics teacher, I've actually believed them. And I thought, wow, that's not magic. I didn't think, wow, that's magic. I thought, wow, they have a very powerful motor. We have such a very powerful motor. Is this ready to run?
No,
Ah,
no, it's not. Hold on, sorry.
So the claim being, if you just put stuff in there, we're putting water in there, and you let it whir around and be its powerful little blade spinning self,
It's not going to do it
it's, what's not doing it?
yet. Go ahead,
Okay.
you're good.
Lager
It's going to churn the water, right? It's going to spin it around, and you're going to have water molecules colliding with each other a lot on a scale much bigger than the lead shot in the glove falling on the floor. They're going to be slamming into each other, slamming into the wall of the container. And I'm like, well, I'm a scientist, I need to verify what's going on in here. Is this really going to get warm enough? There's only one way to find out. I can record the temperature. I've got a thermometer in the liquid. Well, this is kind of dinky. I haven't proven it won't happen yet. Holy smokes!
Look at the pavement.
Yeah. All right, I'm convinced. If I get electricity to jostle around this liquid enough, I can turn electric energy into kinetic energy into thermal energy. These transfers that we think are so wonderful and useful. So let's take it back a long ways from way before the Vitamix. Before I start flaming this up. Somebody found this gas underground and put it in this bottle and delivered it to me. And now, if I mix it with sufficient heat and oxygen on its way out of the bottle, I can get a flame. You hear it. You hear it consuming oxygen and fuel. And I'm gonna, oh yeah. This looks curiously like a little model train engine. This is, no joke, a steam engine. I've got a container full of water, I'm gonna boil it from underneath, and it's gonna build up a head of steam. That's like a very, literal term we have in our everyday language, right? You're gonna turn the water into this amount of steam. Steam wants to take up more space. It's gonna push harder on the container walls, increasing pressure. Pressure is wonderful if you're building machines because it can push on a container wall, and if you've cleverly designed that container to have one side be pushable out and then pullable back in, you've got a piston in a cylinder, and you've got locomotives, you've got this is an external combustion engine, but internal combustion engine is the next step. These have fallen out of favor for obvious reasons at this point. But I've got some steam, I know something's happening. Come on, buddy. Ooh, just need a little nudge. Wow. That's spinning its little heart out. So my piston in the cylinder is right here. I'm delivering steam through this little pipe. And off we go. That seems remarkable. A blowtorch, I can drive a car down the street, right? It's not that easy. So what's happening in here? My slide title's Timing is Everything. Here's where the machinists and the engineers step in and help us out. Physics, engineering combined to make useful stuff. Oh, you're off-gassing. Got a little paranoid about my blowtorch for a second. So, as I said, high pressure steam in the cylinder. It's going to push the piston forward, pushing this part forward. But it's designed in such a way that it says, oh, you're at the end. Let's not have pressure anymore. There's two ways to do it. You douse it with cold water, or you let the steam out. Depressurizes on its way back. Pressurizes forward. Depressurizes on its way back. And you get that going. All I had to do was turn on the blowtorch, right? And then I can go do other things, and a machine is like self-actuating. That's pretty cool. I can make soup with electricity and kinetic energy. I can drive a train down the tracks. What else can I do with this crazy energy thing? Actually, before I do that, that didn't turn. Is that plugged in?
I'll plug it in.
All right.
It's not plugged in.
So here's where a lesser physics teacher would get real murky and technical and go down the electricity and magnetism rabbit hole for you. I'm going to try to stay on the surface and just say, here's what I got and here's what I see, and this is why it's important for an energy demonstration. I've got these You know they're magnets because they're painted red and blue, and they say N and S on them. I've got a powerful magnet. I have a loop of wire. So I've got these 2 prongs of wire. What are those things in? Oh, something I don't want to eat. Mercury. We still use it, despite all evidence to the contrary, because it's the only way we're going to make a connection in a pool, and it can rotate pretty freely, right? So one of my posts is in a little bit of mercury, separated from the other donut of mercury. You can't see that. So these posts have electrical connection all the time, even if they spin. With me? So if I run electricity out the wall socket, through my little blue box down here, and I've got a switch that allows me to turn on electricity and push charges through that loop that's like a square shape on your screen. Okay? So let's see what happens when I do that. Oh, maybe, yeah, there we go. This should be interesting. Whoa. Can you see that on the camera? Wait, I thought it was going to spin. It did spin, and now it's not spinning. Huh. Wait, what? When you run charges through a loop of wire, you turn that loop into a magnet. You've created an electric field inside the loop. So like magnets are these crazy things, right? You start playing with them as a kid, you get them from the Franklin Institute maybe, and you're like, oh, what happens if I put this magnet near this compass? What happens? Wait, the compasses are magnets? There's this invisible force field out there surrounding the Earth, and things tend to line up in certain ways, right? And then they don't unalign unless you push them. That's how compasses work. I hope we've played with compasses. First assignment today, if you've not played with a compass, do that. So what's happening is, the direction of the magnet I make with that loop, it's fixed. If I run current around it this way, it's going to be a magnet that way. If I run current around it the other way, it's going to switch sides and be a this way magnet. North-south, flip-flop. I make magnetism with running current around the loop. So I'm almost satisfied because I made something spin with electricity. I'm like on the verge of having vitamins. But my timing has to be right. Ooh. I don't think I'm going to make soup this way. I can barely spin a coat hanger. So here's what we need. We need what's called a commutator. Sorry for that big word. But that's the word we give for this thing. Can I help my contrast?
Do you want me to do that?
Yeah, it's okay. I don't think we're going to get much. So you might have to take my word for it that I've got 2 pieces of copper insulated between them, and they are connected to leads that make a coil, but they make lots and lots and lots and lots and lots and lots and lots of loops around the thing. So I've mounted one in here.
I don't know if it's visible with some lighting.
Oh, that's much better. Oh yeah, right there. That's the black insulator poking through.
Get the laser.
Separates the Yeah. I think that's good. So now let's try to get a close-up on. I've mounted one, once again, between 2 magnets. So I'm going to try to change the magnetic field. I'm going to change the electricity, the way it flows around these coils, in the presence of a magnetic field. And I'm solving my timing issue by that thing I'm calling a commutator, meaning the leads from the electric box touch the right side of the coil at the right time. That'll have to be good enough for now. and my incompetence is erased by my engineering. I don't know. I've done that 100 times, I'm still impressed. Sorry. Yeah, that's cool, right? But there's no such thing as a free lunch. Whatever's coming out of the wall could spin this doodad. Cool. How does it actually feel to try to run doodads? I've got a generator in here. It looks a lot like a pencil sharpener. Not to you though, right? Maybe your teachers. What happens if I apply a load to what I'm trying to do?
Wait,
Yep.
if there are any students that are sensitive to flashing lights, this is your time to close your eyes or exit the room or whatever you need. Sorry. Don't want to skip that public service announcement.
Yes. So this one is just, I got a red light bulb, incandescent light bulb. You can still buy these, but barely. I guess you can say it's on. And I feel like I just climbed to the 4th floor. That doesn't seem like a great trade-off to me. So, what's happening is, I'm doing what that's doing. I'm spinning coils and or magnets in the presence of the other, right? I can either spin a loop in the presence of fixed magnets, or I can spin the magnets inside the loops. So I'm spinning the magnets inside the loops, and I'm pushing electricity around this circuit marked by the red on my wooden platform. And I can barely talk to you while I'm getting a faint glow from a light bulb. That's not great. We engineer. Oh. Let's electrify some gas that will phosphoresce inside a closed container. And here's where you want to look away if you're sensitive to blinking. I feel fine. This takes way less energy to make light. My efficiency is amazing. It's a strobe light. If I go faster, you gotta have a good eye now. Which is happening when I go faster? Is it brighter, faster blinking, or both?
Is it exhausting?
Yeah, it makes sense that it blinks every time I crank, because I'm physically spinning one of those magnets that has polarity in the coil. So if I spin it faster, it's going through that change faster. And we've done even better. Now when you buy light bulbs, the box says, this thing really uses 8 watts, but it shines like a 100-watt light bulb. Don't quote me on those numbers, but they're close. Oh, that's a breeze. So I don't know. When Boathouse Row went to LEDs, I felt a way about it, but deep in my heart, I knew it was right. Because I now know we are putting way less CO2, like what was in that canister, out into the world. Again, the blinking, because, I'll go back to the red one. Curious thing about incandescent bulbs, they're so fun to play with as a scientist. Not efficient. But no blinking because you're doing a physical thing. You're heating up the filament, and it doesn't have time to cool back down by the time you've done your next crank. So it appears as a soft, continuous glow, as opposed to these others, which are fast on, fast off devices. So, what this demonstration is that, can you get the lights back on?
Yep.
Like, having a load on something matters a lot. And all these transitions of energy we're in love with, they all come at a cost. Every time you like metabolize food, try to pedal your bicycle, you've lost something. We can tell you how many calories you've eaten, therefore how many joules you should have. But the act of spinning your bike wheels and the gears inside have taken away, siphoned off, taxed, if you will, some of those joules or calories. Now, hopefully I haven't let this cool for too long. And we will get our old friend the steam engine back up and running. Bear with me. I know there's steam. It wants to go.
Back in the day, you used to have to crank cars before
Yes.
you turn them on for just this reason. You had to get it going so the timing is right.
Okay.
There it goes.
Ah. I've redone my very impressive steam engine model. And, oh, you say it can run down the tracks, Ryan. Well, it should be no big deal to spin this little fan. No. This machine is so inefficient in those energy transfers. Burning fuel, making steam, turning this, turning that, which is another DC electric motor, to turn this, that it's all used up by the time you want the end result to happen. So efficiency, efficiency, efficiency is always our frontier, right? We're still trying to get homes and devices and automobiles and trains more and more and more efficient.
So timing, right? We got to this idea of timing is everything. Timing is what allows us to do this. There is another really important timed phenomenon that we would like to talk to you about. And that is called resonance. So again, sorry about physics language being specific. When I say resonance, I do not mean the deep resonant voice that I have with gravitas and all of that, right? What I mean is that we have seen that these things have certain rhythms to them, right? That he had to hit the switch at the right rhythm to get it to go. And being able to time energy things allows us to make up for this. So, let's be honest, I look like I could be a son of Moria, right? I'm a fairly stocky person. How many of you think that I could lift Mary above my head? All right, the one person who has seen me do it has raised a hand. All right, so how many of you think that I could lift a person above my head with one hand? Right? That's getting into like, why are you not on strongman competition levels, right? How absurd would it be if I could lift a person above my head with 2 fingers? Right? That's officially bananas. Right? That's not a thing that humans should be able to do. Resonance might allow us to get away with this idea.
Sorry.
Because the beautiful thing about resonance is that I do not need to exert all of that energy at the same time. I don't need to have a singular push from my muscles, converting the starches that I ate for breakfast into energy to push my muscles hard enough to lift a person into the air in one giant push. Resonance allows me to pay into that activity over and over and over again.
Can you tell me when?
All right, so Mary is here on a frightening garage door spring, right? And I am going to push on Mary's foot with 2 fingers.
Oh, I'm letting you know. Oh, I gotta keep my feet right. Sorry. And just so you know, my hands are actually hindering the motion. I'm not pulling, I'm just making sure that my back doesn't fall off. Oh my God. Because if I fall back, this is a different show. And totally YouTubeable.
Yeah. So, Mary is now completely above my head, using only an energy input from my two fingers. But very importantly, I am inputting energy to the system only at very specific times, right? If I push at the wrong time, right, all of this immediately stops. A lot of you probably have some experience with this. If you've ever been, in a playground and wanted to push your friend higher than your head, right, you put them on a swing, right? And we can push someone on a swing to go alarmingly high, but only if you push at the right time. If you push at the wrong time, you're just punching them in the kidneys and they fall off the swing, right? And that is what's going on here. That by using this idea of resonance, I am pushing at exactly the right time for this spring, I can keep feeding energy into the system over and over and over again. And that energy builds up and builds up.
I want one of my classes.
All
Make
right.
sure you got an I beam.
Yeah, first you need the eye beam.
Are we bringing the ladder back? Okay, hold on. I gotta yoink myself up here.
Okay, tell us one.
One more.
Yeah, bring it in.
Bring it in.
All right.
Got it.
So this is kind of
Closer.
one of the classic examples of
Oh, my
resonance.
shirt's in it.
Yeah, sit back down. You gotta sit back down. Sit down or rip
I've
your
lost
shirt
the
off.
shirt this way
Yeah.
once. There we go.
Yeah, it'll eat you.
Oh, and this has to come down. All right, you
Right.
can keep talking.
Great. So this is kind of a classic example of resonance, right? As we've established before, you come here for some of the bigger things because we have the bigger things. This was not the big thing, by the way. The other place that you may have heard of the idea of resonance, right? That we can have, the other place that you've heard of the idea of resonance is probably in music, because that is the most common place that that most of us have played with this idea of waves and energy and timing, right? What is the unit that we talk about for music? Right, like ma, like what unit is that? Right, sorry, that was supposed to be roughly the same volume. But like, ba, 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 like where, like what units are we talking about there? Right, hertz, frequency, notes, something like that. So all of those situations are, I'm getting my vocal cords to vibrate at some frequency, some number of vibrations per second, right? So that gets us into this idea of timing that we're talking about. We are not talking about timing like tempo, like everyone steps on the right foot at the same time. We're talking about timing in terms of how fast you're getting your embouchure to vibrate, your reed to vibrate, things like that. And that's what gets us into pitch and frequency. And Mary is now going to talk us through this idea of having two things in resonance, as opposed to just one spring that we're driving at resonance.
All right, so I have a couple of things going on here. We're going to start with, this is a demo that I forgot to queue up. And, so I have two tuning forks over here. Could you swap out this wine glass, please? I have no grip strength today. But so I have two tuning forks here. And, tuning forks, depending upon the length of things, they're tuned to different notes. And so if I smack this, you guys can hear that, right? It's very exciting. It's on this cute little box where the tuning fork vibrates the box, and vibrates the air inside, which vibrates the air between you and it, which vibrates your eardrum, which is really just a capacitor made out of flesh, right? So, what if I take a tuning fork and I aim it at another tuning fork, though? So I'm going to take this tuning fork, and now I'm going to stop it. I only hit this one. Why is this one making noise? Right? It's a word that Pete was just using. Resonance. This tuning fork is pushing back and forth and pushing back and forth at a frequency that this tuning fork is receptive to. because they're the exact same 440, right? So they are in tune with one another. They are interested in pushing each other back and forth. They're receptive to this. Different materials have different resonance frequencies. I'm so sorry, I'm the only one that can do this demo now because I just licked my finger. But, oh, not that one.
No.
Sorry. Gotta get a different wine glass. Here we go. I mean, drinking glass. But, and I don't know if I'll get it to work, but have you seen people do this before? Take a wet finger and they run it on a piece of glass and it, it starts to resonate. It starts to resonate, right? Ben Franklin invented an harmonica, which was a series of these broken glasses where he could use water and play different frequencies. But if they're all the same material, then why were they playing different frequencies? They have different sizes and things of the like that made them receptive to being pushed at certain energies. So what do I have here? I have a wine glass that is, and can we get that camera on, please?
Yep.
Shoot. I have a wine glass that is right in front of, but not touching, a subwoofer from a car, right? So I have this intricate set of tools here that are not plugged in, I don't think. Come on, yeah, there you go. That I can play frequencies out of here, and that will vibrate the air, which will vibrate the glass, and it's very exciting. All right, so let's turn this thing on. And it is on. All right, let's turn this guy on. And I'll turn it down a little to, oh, I can't read that guy. 9 something. All right, 968 it looks like. All right. And we're in the right ballpark. All right, I'm going to turn this thing on. Oh, isn't that exciting? No, it's not at all exciting. How can we see what's happening here? Ooh, I know a way. What if we put something inside there that we could see its kinetic energy, right? Let's take a look at that. And now I'm going to cue through a few frequencies here because I'm not sure I'm reading that right. It says 968 or 868. I'm going to say it says 868.
864 is what I see.
864? Alright, so I'm not even in the right vicinity. Alright, I know this is agonizing noise. Oh. Oh. You see it? I'm not touching it. There's no wind. We put a blast shield down. Oh, I'm starting to hear something. Oh. We're shaking it. Oh, that's exciting. Isn't that exciting? But if I turn this up a little higher, it dies out. Right? It dies out. Why is that? This glass is tuned to about 864 hertz. It's receptive to a push at 864 hertz. All right, so now, if I want to blow this thing up, I'm going to need to take the ping pong ball out. Why? What do you think? All right, think about a lot of the things we've heard today. Energy can be neither created nor destroyed.
Ping pong ball.
Right? Well, I heard somebody say something. Or was it? Go for it. Right? Energy can be transformed into other forms. What kind of energy am I starting with here? Sound. And what's the ball getting? Kinetic energy. But changing the condition of an object is doing work. And work comes at a cost. Right? So if I'm moving the ping pong ball, the glass isn't getting all of the energy. So I need to take this thing out. And this would be the opportunity where anybody that is sensitive to light, again, may wish to close your eyes or leave the room. You've got a couple of minutes here before we get into turning on a strobe light. So, right, so now I'm going to turn this thing on. And if we look at this, ooh, nothing's happening. This is not exciting at all, right? I can tell you that this is cued to around 864 hertz. Do you know what your eyes see at? You know what your eyes are receptive to? Right?
What kind of frame rates can your eyes see?
Think about how they record films.
Some of you are gamers, I know.
144.
Right, so your eyes stop paying, yeah, anything above 30 starts blurring together and looks continuous. Some people will argue you can go up into the 120s to optimize performance things. It's debated, right?
But your eyes stop caring at a certain point. And at this point, you can't see what's happening. So in comes the strobe light. All right, how does a strobe light work? I'm hoping that everybody that needs to be out is out. I'm going to turn this thing on. It blinks with a frequency, right? This thing only goes up to, I want to say, like 100 hertz. I can't make them match. I can't have this vibrating at, if this is vibrating at 864 and this is vibrating at 864, then we just see the same thing all the time. If this is vibrating at 864 and this is vibrating at 86.4, then I capture it once every 10 cycles. And what's the problem with an even number on a cycle? You're finding it at the same spot every time. So it still looks like it's not moving. So I'm going to cue this to just a little bit off. If I want this to be at 864, I'm going to put this at like 86.0. Just so it's a little bit off. So I'm catching it at a different spot every single time. And I'm sorry, none of it's vibrating right now because I'm getting it cued to a good spot. And 5. All right, 85.9. All right, so we're going to turn this thing back on. And now I'm going to cue this out. Cue it a little bit lower. And can you guys see that vibrating there? I don't know if it is visible on there. I know I see it down here. Let me try turning it up a little. And it's going to get loud. There we go. You see it shaking there? All right, now you can be spared. Thank you. So, resonance is important. Your second bit of homework. Number 1, play with the compass today if you haven't already. 2, Google the Tacoma Narrows Bridge and look for a YouTube video that says Galloping Gertie and see exactly what can happen when you add energy at just the right time. It's a lot worse than a wine glass. So that is our show for you today. We hope you have lots of questions for your teachers.